large molecules, since they are formed from so many small units, that is when small units have joined together on a large scale, and they contribute towards an indispensable portion for our existence. And this is very clear to all of us, that is, the polymers have become integral part of our lives, may it be a toothbrush or car parts. And they have become so popular owing to its certain properties, and they have become so popular that in certain applications they have even replaced the metallic parts, like in the construction of aircraft parts and many other applications, for the construction of toys and many other applications. So if I name a few certain properties that polymers are popular owing to that properties, they are, that is, they are light in weight, they can be molded to different shapes, they are easy to manufacture, even a complex design can be attained in the case of polymers, and the cost is very much effective, like they are not very expensive when we synthesize them, and the desired properties can be attained. So these are the certain properties that make polymers very popular and indispensable portion for our existence. More and more, they are main constituent of our food, that is starch, protein, etc. If we talk of our clothes, they are made up of polyester, nylons, lycra, etc. All these are polymers. The components included in building of our houses, that is wood, cellulose, alkyd paints, that is oil-based paints, and even our bodies are composed of polynucleic acids like DNA, RNA, and proteins, and the monomers in forming the proteins are amino acids. So we can see that the major role played by the polymers in our lives is very obvious. Now, if we come to the definition of polymers, polymers are compounds of very high molecular weights, as they are formed by the combination of very large number of small repeating units. The repeating structural units, they are derived from some simple and reactive molecules known as monomers. These monomers are further linked to each other by covalent bonds. That is, the repeating units, they join together via covalent bonds and result in the formation of high molecular weights. If 5 to 6 monomers join together, they result in the formation of the structures known as oligomers. But if we talk in terms of like thousands and hundreds and even more number of monomers joined together, they result in the formation of polymers. These polymers are also referred to as macromolecules because they are very big in size and they are formed from smaller subunits that join together on a large scale. So we also call them as macromolecules. But here we have to make a very point clear, that is, if we talk strictly on the basis of how do we differ polymers and macromolecules from each other, though they are used synonymously, but polymer always contains same subunits, that is the same repeating units. The monomers in a polymer are of the same type, whereas a macromolecule is a giant molecule that may or may not contain same subunits or monomer units. That is, the monomer units may vary. For example, DNA is a polymer that is formed from all nucleotides as monomers, and in proteins, the monomers are all amino acids. Whereas if we talk of triglycerides, that is fat, they are made up of glycerol backbone and several fatty acid chains. So we can say that all polymers are macromolecules, but not all macromolecules are polymers. Now, coming to the process that involves the formation of polymers, and we call that process as polymerization. How can we define this process, polymerization? This is the process by which the simple molecules, that is the monomers, are converted into polymers. This process is known as polymerization. That is the process in which the different monomers combine together to form polymers, or we can simply say the chemical reaction in which high molecular mass molecules are formed from monomers. This is known as polymerization. For example, many ethylene molecules combine to form a giant molecule of polythene. This is the ethylene monomer, and these ethylene monomers, they polymerize or join together to result a polymer, that is polythene. If you can see this N refers to the number of monomers in the polymeric chain, that how many monomer units have united together to form a certain polymeric chain. This polythene is both a polymer as well as a macromolecule, as it contains a large number of repeating units. Since it is formed on a larger scale and all the monomeric units are of the same type, that is, all the ethylene monomers are involved in the formation of polythene. So polythene is both a polymer as well as a macromolecule. Now, we are in position of defining a term, that is degree of polymerization. The number of repeating units in a polymeric chain is called degree of polymerization. That is, how many repeating units, how many monomers have been joined together to form a certain polymeric chain. We call it as a degree of polymerization. In other words, degree of polymerization is a number that indicates the number of repetitive units, that is monomers present in the polymer. Degree of polymerization, generally we represent it as dP, and it is represented as N. As we can see in the previous slide, this N refers to the degree of polymerization. So the molecular weight of a polymer can be calculated by knowing the value of degree of polymerization. How do we do that? Molecular weight of the polymer is equal to degree of polymerization multiplied by molecular weight of each monomer. That is, if we know what monomer is used in formation of a particular polymer and what is the molecular weight of each monomer, we can evaluate the molecular weight of the polymer. For example, if we are supposed to calculate the molecular weight of polythene polymer whose degree of polymerization value is 100. So, molecular weight of the polythene will be degree of polymerization multiplied by molecular weight of ethylene. Molecular weight of one ethylene unit is 28. That is, so 100 into 28 is equal to 2800. So this is how we can very well evaluate molecular weight of a polymer once we are familiar with the degree of polymerization value and the molecular weight of its monomer that is used up in making that polymer. So next we are coming to the very important part of polymers, that is classification of polymers. That is how we can classify polymers based upon the different criteria. To name certain criteria, first on the basis of origin, that is how do they originate. Second, on the basis of their monomer composition, that is what monomers are used in the composition of that particular polymer. Then on the basis of chain structure, what chains are involved in the formation of the polymer. Fourth, based on the polymerization mechanism, what mechanism is involved in the formation of that particular polymer. We'll see all these classifications in detail. Fifth, based on tacticity, I'll introduce you to all these terms in the subsequent lectures or sessions. Then based on the molecular forces. I'll be taking up this classification one by one in detail, and our further sessions will be based upon these classification of polymers. So to begin with, first on the basis of origin. On the basis of origin, that is, they are natural or synthetic. Natural polymers are naturally occurring polymers that are existing in plants and animals. For example, starch is a polymer of alpha-D-glucose. Cellulose is a polymer of beta-D-glucose. Similarly, proteins, they are polymer of alpha-amino acids. These are certain natural polymers. For example, cotton, natural latex we get from rubber tree is a natural polymer. Similarly, rubber tires and rubber bands are made from rubber, and proteins from eggs and other foods, they are all natural polymers. So though these natural polymers have extra strength and stability, but at the same time, they are very, very expensive and we cannot mold them to our desired shapes always. And to incorporate the desired properties, we need to modify, or we need to look into the methods so that we can synthesize polymers on an industrial scale. So next is the category of synthetic polymers. These are prepared in the lab artificially. For example, polythene, polyvinyl chloride, nylon, bakelite, etc. So the invention of synthetic polymers on industrial scale is a revolution in itself, and it has led to various enhanced applications. For example, synthetic polymers are used in make polythene, used in making bottles, polyvinyl chloride, pipes, polytetrafluoroethylene that are used in making utensils, then polystyrene and polyester, nylon, lycra, etc. These are used in making our clothing material. These are disposable cups that we use. These are CD material. CD material is made of polystyrene. So these are the uses of synthetic polymers. They have really proved to be versatile. Next is on the basis of monomer composition. On the basis of monomer composition, if the polymer is formed from one type of monomers only, that is, if all the monomers in a polymer are identical, for example, n number of A monomers joined together to form a polymer, and as we can see here, all are identical in nature. These are identical monomers. We call them as homopolymer. For example, as I already discussed with you, polythene is a polymer formed from the ethylene monomer units. That is, all the ethylene monomers joined together to form a polythene. And also vinyl chloride, if we take as a monomer, it results in the formation of polyvinyl chloride, that is PVC, that is used in the construction of pipes that are very, very popular. Another type of polymer based upon the monomer composition is copolymer. These are formed by the combination of more than one type of monomers. That is, if we use more than one type of monomer in forming a single polymer chain, we call it as a copolymer. So the general equation of this can be this n number of monomer A combined with m number of monomer B to form a resultant polymer. Now, how these different monomers are arranged within a polymeric chain, we can further classify these copolymers into various categories. But before we proceed this, we discuss these categories in detail. A big question is, why do we wish to incorporate different type of monomers, that is two different monomers on a simple basis, to make a single polymer? The question is very, very straight, and the answer is very simple. That is, we wish to incorporate some desired properties, and we want to incorporate the properties that are suitable for a certain application. For example, if we want desired strength and flexibility in a polymer, then we incorporate two monomers in a single unit. Why do we do this? Because the properties of polymers, they strongly depend upon monomer type. The properties of the polymer, that is, what is the strength, what is the flexibility, what is the flow, what are the flow properties of the polymer, they all depend upon the monomer from which it is formed. For example, monomer A is a bulky monomer that can form a strong bond but with limited flexibility, whereas monomer B is a small monomer with excellent flexibility but poor strength. And if we want a material with good flexibility and strength, that is, we want to synthesize a material that has both good strength and flexibility, then a polymeric chain can be designed containing both A and B monomers. A would give it a strength and B would give it flexibility. But in doing so, we have to be very careful about the relative sizes of both A and B. If the relative sizes of A and B are significantly different, the properties of both the monomers may be lost. If we wish to keep the good properties of both monomers A and B, we have to design a chain so that both the properties are intact. On an industrial scale, industry block length is always controlled to get the desired properties. So once we have discussed why do we wish to incorporate different monomers in a single polymeric chain, now we can see how do we categorize them. One is random copolymers. If the monomeric units are arranged randomly, as you can see in the chain, they are arranged randomly. There is no certain order that is followed here. Similarly, in alternating copolymers, the monomeric units, they are arranged alternatively, as you can see. A, B, then A, B, they are in alternating fashion. Coming to block copolymers, monomeric units are arranged in blocks. As we can see that a block is formed from monomeric unit, one monomeric unit, that is A, that is combined with another block that is composed of the monomers B. Now, next is graft copolymers. In graft copolymers, these are the branched copolymers in which one monomeric units, that is the backbone, is formed from one type of monomers, while the branches are formed from the other type of the monomers. That is, one type of monomers are forming the main chain, while the other type of monomers are forming the branch of that main chain. Now, the advantage of copolymers, as I already discussed with you, they have properties different from the polymers that are made from either of the constituent homopolymers. So it is very advantageous and the desired properties can be incorporated. This is the advantage of using copolymers. Next is on the basis of chain structure. How do we classify this? We classify this as linear polymers, branched polymers, and cross-linked polymers. This will depend upon that the chains are linear, branched, or cross-linked. In linear polymers, the different monomeric units are joined together along the axis via covalent bonds to form long and straight chain. There is no branching involved at any point. So these linear polymers, since they are linear in nature, so they are very well packed. Being very well packed, they have very high densities. For example, PVC, polythene, so they have very well higher densities, and since they proceed in a single direction, they have directionality also. Being well packed, and there is a repetitive nature in them, so they are also crystalline in nature. So this is the category of linear polymers. Coming to branched polymers, in this monomers are joined to form long chains. As we can see, monomers are joined to form long chains with side chains of varying lengths. The side chains are of varying lengths and they are joined at various positions. They are originating from various positions. Since the branches are of varying lengths and originating from various positions, they are irregularly packed. Being irregularly packed, they have low densities. Example, low density polythene, glycogen, etc. Next is cross-linked polymers. They are formed from bifunctional and trifunctional monomers. Bifunctional, trifunctional monomers means they have active sites, 2 or 3 active sites. When various linear chains, they are held together, one linear chain and another linear chain, they are held together by strong covalent bonds, they form a three-dimensional network. They are linked together at various positions, and one chain is connected to the other chain by strong covalent bonds. Since they form a network, and strong covalent bonds are involved in linking one chain with the other, they are hard and rigid and they do not melt easily. For example, vulcanized rubber, bakelite, etc. So this was classification based upon the chain structure. In the next session, we'll be taking up classification based on polymerization mechanism.